In this lecture, I'd like to dive more into acid strength. And so we've already kind of touched on this. We were trying to identify what makes something an acid versus a base, right? And coming out of that conversation, we're like, well, acids have these hydrogens that can be acidic, because then you can break a bond to a hydrogen easily enough. And we were seeing examples where that hydrogen was often bonded to an oxygen, which made that hydrogen more partially positive. And so now we're going to be a little bit more methodical about how we walk through this. We're going to walk through a few different structural features of covalent molecules that help us predict the strength of an acid. We're going to start with binary acids. And then we'll look at oxoacids after that. And so what we see as we start to look at binary acids, which is going to be a hydrogen and then another atom, right? So it's not necessarily connected to an oxygen except for water. And so in all these cases, we have some right here. It's a hydrogen with another element. And so it's either with a halogen or it's with something in group 6. So in these, there are two structural features that really play a role in the strength of the acid. It's the electronegativity of the element that the hydrogen's bonded to. And it's also the bond strength of that hydrogen other element bond. And so it's not really just electronegativity. That's an oversimplification. That is definitely an element of it. But what we're really looking at here is how easy is it to break this bond? And it's going to be when the bond is weak, or when the bond is already partially broken, just because that hydrogen is so partially positive already, it's easy for it to just abandon its electron and become a fully positive charge. So let's talk about electronegativity first. So here our hydrogen is partially positive. And so what we have in that uneven distribution of electron density is that it's mostly on the other molecule. And so that hydrogen's partially positive. And so if that bond breaks and there's a formal charge of -1 on the other element, it's already very electronegative, which means it is easier to support a negative charge. So a very electronegative element like fluorine is going to be more stable as an anion than something that's less electronegative. And so we see this trend right here that as electronegativity increases in binary acids, we see acidity increase. And so we'll see hydrofluoric acid is more acidic than water. We'll see hydrochloric acid is more acidic than hydrogen sulfide. And so we see that those halogens produce more acidic binary acids than something in column 6. But that isn't like the entire picture. So that's definitely one piece. Now we have to weigh the other idea, which is bond strength. And so the idea with bond strength is, well, if it's easier to break the bond to the hydrogen, then it'll happen more often, right? It'll just take less energy to do that. And bond strength, remember, is a measure of bond length, right? So bond length tells us a lot. And that bond length is telling us a lot because it's coming from how far apart those oppositely charged particles are. How close are the shared electrons to the nuclei that they're attracted to? The further apart they are, the easier it is to separate them more, right? The closer they are, the stronger that interaction. And that's coming out of Coulomb's law again, right? Which is the magnitude of the charge. So if it's like +1, -1, whatever, plays a big influence on how much force there is between two opposite charges being attracted to one another. But also that is a function of the distance. So the closer they get, the stronger the attraction, the more energy required to break them. So bond length, as it increases, bond strength decreases. And we see acidity increase. So the longer those bonds, the more distance there is, the more acidic it is. And so we're going to see that happen with large atoms, right? And where are large atoms? They're at the bottom of the periodic table. And so here is our trend right here, that we see a decreasing bond strength as we go down this, the elements that could be bonded to hydrogen. And that's going to lead to an increase in acidity, which means of these binary acids we have here, which are arranged in terms of where the non-hydrogen elements are in the periodic table, the one that is going to be the strongest is this hydroiodic acid. So electronegativity increases going across the periodic table. Iodine is not that electronegative though. Um, but it's so large that it actually has a much weaker bond to that hydrogen, and so it's easier to break. So, continuing on this, we can build off this and say, what are the tools that we're going to use to determine the relative acidity of something? So, we're going to have to balance both of these features. So, it's easiest to do a comparison between two acids and say which one is going to be the stronger of these two. We're not going to give you something, just say, is it strong or weak, like justify it. We'll usually do a comparison at this level. And so the things that we're going to use and weigh and balance. And again, this is one of those gray areas where is it more important to look at electronegativity or bond dissociation energy? It's like, well, it kind of depends how electronegative is and how weak is that bond. So we're going to use the electronegativity chart to look at and compare electronegativities to see which one is greater. And the greater electronegativity element bonded to the hydrogen will be more acidic. And then we'll look at bond strength by looking at bond dissociation energies. We can also use size as well to help predict this. As well, we can use bond length if we need to. It can be a helpful tool. And so these are kind of the pieces of information that we can go into it. So we see as that bond dissociation energy decreases, that bond strength decreases, and we'll be able to see an increase in acidity. All right, let's look at oxoacids. So remember, we're defining oxoacids as the hydrogen that's bonded to an oxygen bonded to something else. And that hydrogen is bonded to something more electronegative from it than it. But when we look at all oxoacids, all hydrogens are bonded to an oxygen. So there isn't an electronegativity difference to that oxygen necessarily. But we do still see an increase in acidity on the periodic table um, that is dependent on the electronegativity of the atom bonded to the oxygen. And so we're having this through molecule effect that the hydrogen's not bonded to the X element, but that X element, if it's very electronegative, it'll have a larger pull on the electrodensity on the oxygen, which will in effect pull more of the electron density from the hydrogen because it's also very electronegative. And so we see that we increase acidity as we go up the periodic table. So when X, right? So when this X is chlorine, it's going to be more acidic than if it is iodine. And then we also see it increase as we go left to right on the periodic table. And so that means it's going to be as the electronegativity of Rx increases as well. So something like chlorine would be more electronegative than something like phosphorus. And so it's going to be more acidic. And so we're really just going to see the electronegativity of that X dictate relative acidity for our oxoacids. And so we're only going to rely on the electronegativity of X to predict relative acidity and not bond strength in this case, like we did with the binary acids. And that's because that relative bond strength between the X and the oxygen, right? It won't play a role in how easy it is to break the oxygen hydrogen bond because we aren't breaking the X to O bond at all. And so that bond strength piece really only relies on or tells us something about how one bond will break, right? So electronegativity can have this through molecule effect, but the bond dissociation energy or the bond strength is only going to be important for the acidic hydrogen itself. But there is another feature to oxoacids that's interesting that can increase its acidity, and that is the number of oxygens attached to that X molecule. So we have a hydrogen bonded to an oxygen bonded to some other element, like nitrogen in this case. So here we've got that X is our nitrogen. Then, if that X, so in this case, nitrogen, is bonded to more oxygen atoms, they're going to be bonded to things that are pretty electronegative. And so there's going to be even more of this through molecule pulling of electron density away from that hydrogen atom, which is just going to make it more partially positive. And the more partially positive that atom is, the easier it is for it to dissociate, for it to be donated, for it to transfer to another molecule. And so, as we see an increase in the number of oxygens bonded to the X atom, the more acidic we see our hydrogen. And so, in this case, comparing nitrous and nitric acid, we have more oxygen atoms bonded to that nitrogen. And so, our nitric acid is going to be more acidic. So, given these trends for oxoacids, here's something for you. Which is the stronger acid here? You can pause and think about this. Try to formulate an idea and then come back to the video. So when I look at these, what I notice is they're oxoacids, right? So let's just take two of the hydrogen, one of the this hydrogen here and this one here. So we'll just compare these two. Which one of those is a more acidic hydrogen? Which one's more likely to break the bond to the oxygen? So I note that they're both oxoacids. Actually, they're both carboxylic acids, right? So that hydrogen is bonded to an oxygen in both cases. They're also both have X is equal to carbon, right? And carbon is not that electronegative. So, all right, so there's nothing different about this yet, right? Hydrogen bonded to oxygen, bonded to carbon. All right. So then what about the number of oxygens, right? Well, there's one oxygen bonded to the carbon other than the oxygen that the hydrogen's attached to. So it has the same number of oxygen atoms. So all of these things are the same. Will they have the same acidity? They don't. So if you go and measure, so the methane dial, like it's a theoretical calculated value, because this is an intermediate, like it doesn't exist for very long. But this formic acid, this is acidic. It's a weak acid, but it's a pretty strong weak acid. So this one is more acidic right here, which is crazy, right? So all of these things are the same, but this is the one that's more acidic. We'll talk about comparing their pKa's to talk about how we know this. Like when we measure it, what are we comparing? But one of the big differences here is this double bond, right? And we have this like this kind of carboxylic acid motif is important. So one of the things that is different here is that we have a double bond to the oxygen that we don't have in our other molecule. So what I'd like you to do now is imagine these have both lost their oxygen and ask yourself which one is more stable. I'm going to draw out what these would look like. All right, so comparing these, they both have an oxygen that's negative, they both have an oxygen that's neutral, but one is significantly more acidic than the other. And what it comes down to is which one of these is more stable. So which conjugate base is more stable? It's the conjugate base of our formic acid. And that's because it can form a resonance structure. And that will stabilize, it'll delocalize this negative charge. So this is a delocalized formal charge that's spread out from that oxygen to the other oxygen. Whereas here, this formal charge, this is localized. There's no resonance structure. So all that negative charge is localized on that one oxygen. And oxygens are really good at, like, they're pretty electronegative, so they can handle negative charge, but it's far more stable to delocalize that over another oxygen as well. And so that resonance stabilization stabilizes the conjugate base, which makes it much more favorable for that hydrogen oxygen bond to break, which makes the formic acid much, much more acidic. And so when we're really ultimately evaluating what is acid, like the structural features of acid strength, we also have to be evaluating what are the structural features of conjugate base stability to support that hydrogen being lost.